All right, this is going to be the trig substitution lesson, and this is the mother of all integration techniques. It's by far the hardest one. I want you to just see the three integrals that I wrote there. This is the introduction, and this is what they look like. They have some nasty radicals in them, and I also want to point out, I'm going to write one that will look similar. Now, you may not recognize it, but the one I just wrote is a U substitution integral, right? On the bottom of that, if I rewrite the bottom this way, maybe it's easier to see. And then this would be the U. And if you took its derivative, right, you would get negative 2x. And that kind of matches to the top, right? You'd have that derivative there. What the problem is if I put an x squared here, then this doesn't work. And that's what you have here. You also have one there. Now that last one, I mean, I put a 1 there. It's still not going to work, right? Because the derivative of that would be 2x, but they'll usually put something nasty here, like x cubed. So let me do that. These are very, very difficult, and they require a lot of work. And there's so many places you could go wrong. The idea is simple. Implementing that idea is incredibly complicated. You're going to replace all of the x's with trig functions. That's the whole reason that we spent so much time doing trig integrals with the sines and cosines, the tangents and the secants. Okay, so at this point, I'm going to remind you about our famous identity. Sine squared plus cosine squared is 1. Now, if you were to subtract the sine squared over to here, right, that would mean that cosine squared is 1 minus sine squared. Now, again, if you look at these, look at that. They look exactly the same. You have 1 minus the thing squared, 1 minus the thing squared, except that sign. So if somehow within the problem, right, this is how the game is going to be played. You want to put where the x is, you want to put the sign, so that you would have 1 minus sine squared. And then what you would want to do is use this identity and put the cosine squared, right? Because 1 minus sine squared is equal to cosine squared. And then you have square root, right? Square root. And they cancel each other out, and you would get rid of the radical with just cosine. Now, this is really important. I haven't done it yet, but we're not going to call this x because I started with x. You have to replace this with a theta. But this is, I want to show you the idea before I talk about that even insanity. You're going to replace the radical with one of the trig identities that we already know. Then you're going to use that trig identity to get rid of the radical. That's the problem with every one of those integrals, is that those radicals screw up the whole thing. The goal is to replace all the radicals with trig functions. So the radicals go away, and then you're left with a bunch of trig functions. You're left with sines, cosines, tangents, and secants. You cross out as many as you can, and then what you're left with is a trig integral that you've already done that either has sines and cosines or tangents and secants. That's why you do those techniques before you do this one. And then after that, there's even more fun, but we're not there yet. So this is the idea. So I'm going to write the ones that we're supposed to know, right? We know that this looks like 1 minus sine squared. So that would mean that you would pick x to be, now this is the part that it's going to get a little more complicated. I'm going to just write sine theta because I did this deliberately. I cannot say x equals sine x. Right, you're making a major change of variable here, right? You're replacing the x's with trig functions. So you can't call that angle x. Now, they don't call it y. They don't call it, they use the Greek letter, okay? So this is just how they do it. So you would put, whenever you see something that looked like that, no matter how that integral looked, I mean, it could look really crazy, but it doesn't matter how it looks. They might have a 4 there. And I'm going to show you how to handle that. But it's the same, it looks like that. Something minus something squared. This one is squared plus something. This one is squared minus something, right? So you see that they're all different, right? That's 1 minus the squared. Squared plus 1, squared minus 1. But these could be different numbers. This could be a 9. This could be a 16. They have to be perfect squares. How else are you going to take a number out of the radical if it's not a perfect square, right? They'll have like a 4, a 9, a 16 there. So they're always going to be that. So now when you see that one, hopefully what you recognize is that this looks like tan squared plus 1, right? Squared plus 1. So that's your identity. So in this case, you would pick x to be tan theta. So what you would do is you would put tan there. You'd get tan squared plus 1. I mean, I'll even show you. I'm going to be doing this in examples, but you would put tangent there for x, which gives you tan squared, right? You're not putting tangent squared there. You're putting tangent there, and you're going to square it, right? So when you square tangent, you get tangent squared. But tangent squared plus 1 is secant squared. This is why it works, because you always get a square. And then the square and the square root cancel out. And whoops, sorry, I put x instead of theta. I'm yelling at you not to do x. And I put it there. So when you take the square root of secant squared, you just get secant. And again, it would come out. This is why this always works. You're always putting in one of those, they call them Pythagorean identities because they're all squares, right? It's all based off that sine squared plus cosine squared one. So you always have squares, so they always go away. And this last one looks like this one. Which again, we were using these during the trig integrals. We constantly had to make substitutions during those trig integrals. So in this case, you would pick x to be secant theta. Now, the nice thing, there's a reason they don't do 1 minus cosine. When you take, remember, taking the derivative of cosine gives you negative sign. Here, if you were to take this derivative, right, you would get cosine theta. Now be careful, d theta, right? It has to match. It's the variable's theta now, not x. This derivative would be secant squared theta d theta. And then you know his derivative, secant theta tan theta d theta. And then what you would do is you would put this where the dx is, right? Dx gets replaced by that. So you would put cosine theta d theta right there, which would basically be on the top of that fraction. You would, everywhere you see x, you put sine. You'd have sine there and you'd square it, so you'd have sine squared on the top. You'd put sine there, so you get sine squared there. You simplify that radical. That step is very nasty. You got to be super careful when you do it. You'll see. That's why I'm not doing these. This is just a lesson. I'm going to do the examples, and I'll do them very carefully. But that's the idea. All the x's go away. They get replaced with sines, cosines, tangents, and secants. Never cusc and cot, because those derivatives are nasty. They're negatives of each other, so you don't want those. You don't want any part of that. Everything's nice and positive. Derivative of sines, cosine, positive. Derivative of tan, secant squared, positive, right? You don't have any negative signs that you have to worry about switching things around. It would make it really complicated. Now, unfortunately, there's another part to this. So as I said, the goal is going to be take everything with x, put sines, cosines, tangents, and secants, right? Use those identities, replace, kill the radical. That's the goal. The goal of these problems is to kill the radical. You're using a trig identity with the squareds so that you will end up with a squared here. Like, in that case, you'll end up with cosine squared, and then the square root and the square go away, and you just get cosine. So you're going to do that to all of them. So the radicals will be gone. Now you get to the end of the problem. At the end of the problem, you're going to have something like this. I mean, I'm just, making up something. Suppose you do the problem and you end up here. Right? You make your trig substitution. That's why they call it a trig substitution. You make your trig substitution, you simplify the radical, and you get here. Now you have to find the antiderivative of that. Now remember, the derivative of cotangent is negative cos squared. Now plus c, blah, blah. So you get here. You're not done. You think you're done, but you're not done. My original problem had x's in it, and I have to make it look like what it started as. So each one of these has to be put back into that form. So you have to replace this with x's, and there's only one way to do it. Now, in the very beginning of the problem, you make a substitution. Yeah, I'm drawing a right triangle. So in the beginning, you either did sine, tan, or secant, right? Here, you would pick x to be sine. Here, you would pick x to be tan, and there it's secant, because those match up to the identities, right? 1 minus sine squared, tan squared plus 1, and secant squared minus 1. So you've made those substitutions. So in the beginning, you have something like this. I mean, it's not going to look like that. I just did this for emphasis. If you had something like that, right? Remember that cos and sine go together. So actually, you wouldn't have had that. You would have something like this, right? In the beginning of the problem, you would make a substitution, and it would look like that. Now you have to remember that sine goes with the opposite side over the hypotenuse. So in relation to that angle, remember, this is adjacent, this is opposite, this is hypotenuse. And I bet you thought you'd never see this again. So opposite side is going to be 3. Hypotenuse side is going to be x. And what you have to do is you have to figure out what the missing side is. Because I need, right? I did this integral and I got this answer. I need to put this back in terms of x. So I have no choice at the end of these to draw a right triangle. Fill in the three sides and read off what this is. Now, this side always ends up, now remember, you know that a squared plus b squared equals c squared, right? A, B, C. C is always the hypotenuse. So you can do this kind of quick. You know, C would be x. It doesn't matter which one you call A and B, just for simplicity, I'll call B that. So that would be 9, right? You get 3 squared. Now remember, you're solving for that bottom side. I'm calling that A. So you would subtract 9 over, right? And then you take the square root of that. So that's what that missing side would be. But I'm going to give you a super duper secret hint. No matter what you start with, this thing that's missing will always be, like if it was this problem, this side would have been radical x squared plus 1. If it was this problem, this side would have been radical x squared minus 1. If it was this problem, it would have been radical 1 minus x squared. Whatever radical, this is really important, it saves you trouble. Whatever radical was in the initial problem is the side of that triangle that you don't have. So you don't do what I just did with a squared, b squared. It's unnecessary. You just take whatever this was and put it on the missing side. You're going to have a thing in the beginning. It's either going to be sine, tan, or secant. Now, when it's secant, you got to be careful, right? Because you have to flip that to get cosine. So sine, opposite hypotenuse, you put those two sides there. The missing one, you always put whatever was in the beginning. Now, I don't have one like that. I'm just showing you. In the example I made up, that would have been the missing side. Now, I want cotangent. I don't know cotangent. I know tangent. I know tangent is opposite over adjacent. Now, in my, right, TOA, your SOHCAHTOA, tangerines or apples. This is what I teach my 1275 students when I do trig, right? I make acronyms. So tangent is tangerines or apples, or technology or art, whatever you like. So opposite adjacent. So that's what tangent would be. Tangent would be the opposite side over the adjacent side. But I don't want tangent. I want cotangent. I'll put my plus c in a minute. So all you have to do is just flip that over, right? So cotangent would be radical x squared minus 9 over 3. And then I would put my plus c there. So you start with that question. You make a trig substitution, either sine, tan, or sec. You pop them in there, you use the identities, simplify the radical so it goes away. Simplify the integral as much as you can until you get down to the point where you can integrate it. Then you integrate it. After you integrate it, you got to draw a triangle. Put the sides there. And then read off whatever trig dude you got when you integrated. You might have got sine, you might have got cosine, you might have got cotangent, you might have got whatever. Whatever it is, you integrated, and then you got to go put the problem back to the way that it was, because it started off with radicals in it, and it started off with x's in it. So if it's not obvious to you watching this, really long, nasty questions. And since there are 3 types, there will be 3 on the test. I have to make sure you can do each type. And also, you end up with trig integrals that you've already been working on. That's kind of the whole point of these. They require a lot of work. So again, you're going to watch me. I'm going to do, each video I do is going to be one example. They're that long. If I tried to do 2 or 3 of them in a single video, it would be ridiculous. You'd have a video that's 45 minutes long. So I'm going to do one at a time in the video. And you'll see what I'm trying to explain. It'll make more sense when you watch me do it. But this is the idea of the problems. Okay.